These are the planets that drift through the galaxy with no sun to orbit, no star to warm them, and no system to call home. And this is the story of how astronomers found them, what they're made of, and whether anything could possibly survive on one. There may be billions of these wandering worlds in the Milky Way alone, and some scientists think there could be more of them than there are stars. Before we get into it, if you're enjoying this kind of deep dive, hit like, subscribe, and drop a comment telling me where you're watching from and what you're doing right now, because I genuinely love seeing who's out there listening to this. Now let's get into it. Picture every planet you've ever heard of: Mercury, Venus, Earth, Mars, Jupiter, all the way out to Neptune. Every single one of them has something in common, and it's so obvious that it's easy to forget it's even a feature of how planets work. They all orbit something. They all have a sun. Our 8 planets circle the same star, and when astronomers started finding planets around other stars in the 1990s, the same pattern held. A planet, by the basic definition most of us grew up with, was a thing that went around a star. Except that turns out to be wrong, or at least incomplete. Scattered across the Milky Way, there are worlds that don't orbit anything at all. No sun rises or sets on them, because there's no sun to begin with. They don't have a year, because a year is defined by a trip around a star. And these worlds aren't taking that trip. They are simply moving through the dark, on their own, sometimes for billions of years, carrying whatever heat they were born with, and slowly losing it to the void around them. Astronomers call them rogue planets, free-floating planets, or isolated planetary mass objects, depending on which paper you're reading. And all 3 names are describing the same basic idea: a planet untethered from a star. This isn't a hypothetical category invented for science fiction. It's a real, growing field of astronomy, with real telescopes pointed at real patches of sky, finding real objects that fit this description. Some of these planets were born the normal way, in a disk of gas and dust around a young star, and then got violently kicked out of their own solar system by gravity. Others may have formed completely alone, condensing out of a collapsing cloud of gas, the same way a star does, just without enough material to ever ignite as one. Either path leads to the same fate: a planet-sized object, drifting through interstellar space, belonging to nothing. So how do you even find something like that? A planet glows, faintly, with leftover heat from its formation, but it doesn't shine the way a star does, and it isn't lit up by a nearby sun the way Earth or Mars are lit up by ours. Finding a rogue planet means finding an object that is, by definition, about as dark and quiet as something that size can be. And yet, over the last 2.5 decades, astronomers have managed to do exactly that, again and again, using methods that sound almost too clever to work. There are 2 main ways scientists have managed to spot these wandering worlds. The first is called direct imaging, which is exactly what it sounds like: pointing a powerful telescope at a patch of sky and looking for the faint residual glow of a young planet that's still warm from its own formation. This only works for planets that are relatively young, because older rogue planets cool down and fade until they're essentially invisible. The second method is called gravitational microlensing, and it's a far stranger trick. When a rogue planet happens to pass directly between Earth and a much more distant background star, the planet's gravity bends and focuses the star's light, causing it to briefly brighten in a very specific, very telling way. Astronomers watch millions of stars, night after night, waiting for one of them to flicker in exactly the pattern a passing rogue planet would create. The catch with microlensing is that the event happens once, and then it's over. The planet has already moved on, and there's no second chance to look at it directly. For a long time, this meant astronomers could prove something planet-sized had passed by, without being able to say much about it at all, not its distance, not its precise mass, sometimes not even whether it was a planet or something else entirely. That uncertainty defined the field for years, and that's exactly where the story of rogue planets really begins, not with one dramatic discovery, but with a slow, 2-decade-long accumulation of strange detections that gradually convinced astronomers this wasn't a fluke, it was a population. The first hints came in the year 2000, when astronomers detected the earliest signs of what we now call a rogue planet, a free-floating world orbiting no star at all. At the time, this was a strange enough result that it didn't immediately reshape how anyone thought about planets. It was a single odd data point, a planet-sized object with no star nearby, and the natural question was whether it was a fluke of observation, a misidentified brown dwarf, or something genuinely new. One of the early candidates from this period was an object called CHAR 110913-773444, and even its discoverers weren't entirely sure what they were looking at. It might have been a planet that formed around a star and was later ejected, or it might have formed on its own, condensing directly out of a gas cloud the way a star does, just without ever gathering enough mass to become one. Both explanations remain on the table, and that ambiguity turned out to be one of the defining features of this entire field. When you can't see a star next to an object, you lose most of the easy clues that normally tell you how it came to be. Around the same period, astronomers turned their attention to an object called OTS-44, a very young free-floating planetary mass body that gave them a much clearer picture of what was actually happening out there. Using the Herschel Space Observatory and the Very Large Telescope in Chile, researchers studied OTS-44 in far-infrared light and found something remarkable. The object was surrounded by a disk of material containing at least 10 times the mass of Earth, the same kind of structure you'd expect to find around a forming star, just on a smaller scale. Spectroscopic observations using an instrument called Symphony, also on the Very Large Telescope, showed that this disk was actively accreting matter, meaning it was still feeding material onto the object, the same active growth process seen in disks around infant stars. What this told astronomers was significant. The basic physical processes that build stars, the same processes that gather gas and dust into a spinning disk and slowly feed it onto a growing central body, were happening here too, on an object with only a few times the mass of Jupiter, floating completely alone with no star anywhere nearby. Planet formation, it turned out, didn't necessarily need a star's gravity to organize the process. A small cloud of collapsing gas, left to its own devices, could apparently do something remarkably similar all by itself. These early detections planted a question that would drive the field for the next 2 decades. Were these isolated objects rare oddities, occasional planets that got unlucky and were thrown out of their home systems, or were they common, an entire hidden population of worlds that standard planet hunting techniques simply weren't built to find? Because here's the thing about the way most exoplanets get discovered. The two most productive methods, watching for a star to dim slightly as a planet crosses in front of it, and watching for a star to wobble as an orbiting planet tugs on it gravitationally, both require a star. Take the star away, and those methods stop working entirely, which meant that for years, astronomers may have been counting only the planets that happened to still be attached to something bright enough to study. Anything that had drifted free was, by the nature of the search methods being used, almost invisible to them. That changed in October of 2013, when a team led by Dr. Michael Liu of the Institute for Astronomy at the University of Hawaii at Manoa announced the discovery of an object that would become one of the most famous rogue planets ever found. It was named PSO J318.5-22, a string of characters that sounds more like a parking space than a planet. But the object itself captured public attention in a way few astronomical discoveries do. PSO J318.5-22 sits just 80 light-years from Earth, practically next door in cosmic terms, and it has a mass only about 6 times that of Jupiter. It's young too, by planetary standards, having formed a mere 12 million years ago, which made it something close to a newborn when it was found. The discovery was published in the Astrophysical Journal Letters, and the team identified it from its faint, unusual heat signature, picked up by the Pan-STARRS 1 Wide-Field Survey Telescope sitting atop Haleakala on Maui. What made PSO J318.5-22 stand out wasn't just that it existed, it was how it was found. The researchers weren't even looking for rogue planets when they came across it. They were searching for brown dwarfs, the dim, failed stars that never gathered enough mass to ignite nuclear fusion, which tend to be very faint and unusually red in color. PSO J318.5-22 showed up in that search as an outlier, redder than even the reddest known brown dwarfs, which made the team take a much closer look. Follow-up observations using other telescopes in Hawaii revealed that its properties closely matched those of young gas giant planets found orbiting other stars, except this one had no star. By tracking its position over the following 2 years, using the Canada-France-Hawaii telescope, the team was able to directly measure its distance from Earth and determine that it belongs to a collection of young stars known as the Beta Pictoris moving group, a loose family of stars, all roughly the same age, that formed together about 12 million years ago. One of the stars that gives the group its name, Beta Pictoris itself, has its own young gas giant planet in orbit, which gave researchers a useful point of comparison. PSO J318.5-22 looked like it belonged in that same family of young worlds, with one crucial difference. Every other member of that family had a star to call home, and this one didn't. Michael Liu, the astronomer who led the discovery, put the significance of the find simply. "We have never before seen an object free-floating in space that looks like this," he said. "It has all the characteristics of young planets found around other stars, but it is drifting out there all alone. I had often wondered if such solitary objects exist, and now we know they do." That last line is worth sitting with for a second, because it captures something important about how this entire field developed. This wasn't a discovery anyone stumbled into by accident in the purest sense. Astronomers had wondered, theorized, and modeled the possibility of isolated planets for years before this. PSO J318.5-22 was the moment that wondering turned into knowing. Niall Deacon of the Max Planck Institute for Astronomy, a co-author on the study, pointed out something else that made this discovery valuable, beyond just being a curiosity. Planets that orbit a star are notoriously difficult to study directly, because they sit so close to an object that vastly outshines them. Imagine trying to photograph a firefly sitting an inch away from a lighthouse beam. That's roughly the challenge of directly imaging a planet next to its star. PSO J318.5-22 is not orbiting a star, so it will be much easier for us to study, Deacon explained. It is going to provide a wonderful view into the inner workings of gas giant planets like Jupiter shortly after their birth. In other words, the very thing that makes a rogue planet sound desolate and strange, its complete isolation, is what makes it scientifically valuable. With no blinding star to interfere, astronomers can study its atmosphere, its temperature, and its composition in detail that would be nearly impossible for a planet still locked in orbit around its sun. A few years after the initial announcement, in 2016, astronomers returned to PSO J318.5-22 for a closer look, and the picture got a little more refined. New measurements using spectra from the Gemini telescope found the object to be slightly more massive than first thought, at about 8.3 times the mass of Jupiter, with a temperature near 1130 Kelvin, hot enough to glow faintly in infrared light, even with no star to warm it. The same observations showed it rotating somewhere between roughly 5 and just over 10 hours, a spin rate fast enough to flatten the planet slightly at its poles. This kind of refinement is normal in astronomy. Early measurements of a faint, distant object are rarely the final word, and as instruments improve and more data comes in, numbers get adjusted. The 2016 study placed PSO J318.5-22 in context alongside 2 other young planets in the same Beta Pictoris moving group, 51 Eridani b and Beta Pictoris b, giving researchers a small but valuable set of planets, all born around the same time, all useful for comparing how giant planets evolve in their first few million years of existence, whether they happen to have a star or not. PSO J318.5-22 mattered because it proved a single, dramatic point. A young, fully formed planet really could exist with no star at all, drifting through interstellar space, glowing faintly with its own residual heat, completely on its own. But proving that one such planet existed didn't answer the bigger question that had been building since the year 2000. Was this planet an extraordinary exception, a one-in-a-billion oddity that happened to be close enough and young enough to spot? Or was it the visible tip of something much larger, an entire hidden population of similar worlds scattered throughout the galaxy, most of them simply too old, too cold, and too faint for any telescope to catch? To answer that question, astronomers had to go back to the other method, the one that doesn't rely on a planet still being warm enough to glow. They had to go back to microlensing, and to the patient, statistical work of watching millions of stars at once, waiting for the universe to hand them an answer in the form of a flicker. That patient, statistical work had actually already been underway before PSO J318.5-22 made headlines, and it came from a different direction entirely. In 2011, an astrophysicist named Takahiro Sumi, working at Osaka University in Japan, published a study alongside colleagues from two major microlensing collaborations, the Microlensing Observations in Astrophysics Group and the Optical Gravitational Lensing Experiment. Together, these teams had spent years watching the same patch of sky, night after night, monitoring 50 million stars in the Milky Way for the telltale brightening that signals a gravitational lensing event. They used two telescopes to do it, the 1.8-meter MOA-2 telescope at Mount John Observatory in New Zealand, and the 1.3-meter University of Warsaw telescope at Las Campanas Observatory in Chile, both positioned to give continuous coverage of the galactic center, where star density is highest and lensing events are most likely to occur. Out of that massive monitoring effort, the team recorded 474 separate microlensing incidents. That's already a substantial haul on its own, representing years of careful observation and an enormous amount of data processing. But within that pile of 474 events, 10 of them stood out as unusual. They were short, brief flickers, over almost as soon as they began, consistent with something planet-sized passing in front of the background star, rather than something star-sized. And crucially, none of these 10 brief events showed any sign of a host star nearby. No slower, longer brightening that would indicate a star's gravity was also involved. Just the planet, alone, doing its own lensing. From that handful of short events, against the backdrop of everything else they'd observed, Sumi and his colleagues made an estimate that, at the time, was genuinely startling. Based on the rate at which they were finding these starless, planet-sized lensing events, they calculated that there are nearly 2 Jupiter-mass rogue planets for every single star in the Milky Way. Stop and actually let that sink in for a second, because it's easy to read past a number like that without absorbing what it means. The Milky Way contains somewhere in the range of 100 billion stars. If the 2011 estimate held up, that would put the number of Jupiter-mass rogue planets somewhere in the range of 200 billion, just for objects roughly the size of Jupiter, not counting smaller rocky worlds that would be even harder to detect, and, by most formation models, considerably more common. That number reshaped the conversation. It was no longer a question of whether rogue planets existed, since that question had been more or less settled by direct detections like OTS-44, and would later be cemented by PSO J318.5-22. The new question was how common they actually were, and the 2011 estimate suggested the answer might be staggering. But science doesn't usually stop at the first big estimate, and it didn't here either. In 2017, a researcher named Przemek Mróz, working at the Warsaw University Observatory, led a follow-up study with access to roughly 6 times the statistical data that the 2011 team had used. More years of observation, more microlensing events recorded, more stars monitored, all feeding into a more refined picture. And that refined picture told a somewhat different story. Mróz and his colleagues set an upper limit of about 0.25 Jupiter-mass free-floating or wide-orbit planets per main sequence star in the Milky Way. That's not 2 planets per star, that's roughly a quarter of a planet per star, an estimate nearly 8 times lower than the 2011 figure. This is worth pausing on, because it's a great example of how astronomy actually works when you're trying to count something you can barely see. The 2011 estimate and the 2017 estimate aren't necessarily a case of one being right and one being wrong. They reflect different amounts of data, different statistical assumptions, and the genuine difficulty of converting a handful of brief, ambiguous flickers of light into a confident galaxy-wide population count. What both studies agreed on, despite landing on very different numbers, is the basic shape of the picture. Jupiter-mass rogue planets are not vanishingly rare oddities. They're a real, substantial population, even if pinning down the exact size of that population remains genuinely difficult with the tools available at the time. And there's another wrinkle worth mentioning, one that came directly out of this microlensing research. A separate study, examining hypothetical objects considerably smaller than Jupiter, suggested the number of rogue planets could be up to 100,000 times the number of stars in the Milky Way. That figure covers much smaller, harder to detect bodies, and it comes with far more uncertainty attached to it than the Jupiter mass estimates. But it points at something important. The smaller and more numerous a class of object is, the harder it becomes to actually find and count, and the gap between what's been confirmed and what might actually be out there only grows wider as you move down the mass scale. Put all of this together, the 2011 estimate, the 2017 refinement, and the speculative smaller object study, and you get the range that astronomers still cite today. The Milky Way may hold anywhere from billions to trillions of rogue planets. That's not a typo or an exaggeration for dramatic effect. That's the actual working range scientists use, and the gap between billions and trillions is itself a measure of just how much we still don't know. It's also worth understanding why these planets are so much harder to detect than even the smallest exoplanets orbiting nearby stars. Astrophysicist Andrzej Udalski of the University of Warsaw, who has worked extensively on microlensing surveys, explained the underlying theory behind these big numbers when speaking about a separate rogue planet discovery. Theoretical models of how planetary systems form suggest that free-floating planets should be extremely common throughout the galaxy, he said, potentially even outnumbering stars by several times over. The logic behind that claim comes down to how violent and chaotic the early years of a planetary system actually are. When a young system is forming, multiple planets often jostle for stable orbits. Gravitational interactions between forming worlds can fling smaller planets outward with enough force to escape their star's gravity entirely, and passing stars in dense stellar nurseries can disrupt nascent systems before they've even finished settling into their final shape. Every one of those chaotic processes has the potential to produce a rogue planet. Multiply that by the sheer number of planetary systems that have formed and evolved over the roughly 13 billion-year history of the Milky Way, and the idea of rogue planets outnumbering stars starts to look less like an exotic claim and more like a natural consequence of how messy planet formation actually is. There's also the second formation pathway, the one hinted at by OTS 44 decades earlier. Planets that never had a star to begin with, born directly from the collapse of a small cloud of gas, the same basic process that builds a star, just on a scale too small to ever ignite nuclear fusion. Some of the rogue planets out there were almost certainly born this way, never orbiting anything at all, never getting ejected from anywhere, simply forming in isolation from the start. Untangling how many rogue planets came from violent ejection versus solo formation is one of the open questions that has kept this entire field active for the past 2 decades, and it's a question that wouldn't get a clearer answer until astronomers turned a much more powerful instrument toward one particular patch of sky, the dense, churning stellar nursery known as the Orion Nebula. Before we get to that though, it's worth circling back to the Upper Scorpius region, because in December of 2021, astronomers used many of the same archival techniques pioneered by these microlensing surveys, combined with newer direct imaging data, to deliver one of the single largest hauls of rogue planets ever announced at once. On December 22, 2021, a team of astronomers announced they had found somewhere between 70 and 170 new rogue planets, every one of them roughly the size of Jupiter, sitting together in a star-forming region called the Upper Scorpius OB Stellar Association, located just a few hundred light-years from Earth. That single announcement nearly doubled the total number of rogue planets known to science up to that point. The research was led by Nouria Mireille-Roig and Hervé Bouy, both astronomers at the University of Bordeaux in France, and it was eventually published in the journal Nature Astronomy. What makes this discovery especially impressive is the sheer scale of the effort behind it. The team didn't point a telescope at the sky for one night and get lucky. They combed through 80,000 wide-field images, collected over a span of 20 years, drawing on archives from all 3 of the wide-field images used by the Canada-France-Hawaii telescope over that period, an instrument called Megacam, another called WIRCam, and an older, now decommissioned camera known simply as the 12K. On top of that 2-decade archive, the team layered in data from the European Space Agency's Gaia satellite, a spacecraft built specifically to measure the precise positions and motions of more than 1 billion stars across the galaxy. Combining ground-based archives spanning 20 years with space-based positional data from Gaia let the researchers do something that simply wasn't possible before. Track the tiny, almost imperceptible motions of extremely faint objects across the sky over a long enough baseline to confirm they were real, nearby, and moving the way a planet, rather than a distant background star, would be expected to move. Miret Roig described the method in her own words. "We measured the tiny motions, the colors and luminosities of tens of millions of sources in a large area of the sky," she explained. "These measurements allowed us to securely identify the faintest objects in this region, the rogue planets. Tens of millions of sources, sifted down to a final count of somewhere between 70 and 170 confirmed rogue planets. That ratio alone gives you a sense of just how much painstaking elimination goes into a discovery like this. You're not looking for a needle in a haystack so much as you're looking for a specific, extremely faint needle in a haystack made of tens of millions of other needles that all look almost identical at first glance. The reason the final count comes out as a range, 70 to 170, rather than one clean number, comes down to a genuinely tricky problem in observational astronomy: the relationship between an object's brightness and its age. The team didn't have direct mass measurements for these objects, since direct mass measurements require either a star to orbit, which these objects don't have, or an extraordinarily lucky and rare microlensing parallax event, which hadn't happened here. Instead, they had to rely on brightness as a stand-in for mass, and brightness is closely tied to age. The longer a planet-sized object has existed, the more it cools down, and the dimmer it becomes. So the question of how many of these faint objects are actually planets, rather than slightly more massive sub-brown dwarfs, depends heavily on how old the studied region actually is, and that age comes with its own uncertainty. If the upper Scorpius region is on the older side, the brightest objects in the sample are more likely to sit above the roughly 13 Jupiter mass boundary that separates planets from sub-brown dwarfs, and the planet count comes in lower. If the region is younger, more of those bright objects fall safely within the planetary mass range, and the count climbs toward the upper end of the range. That uncertainty is exactly why the final published number wasn't a single figure, but a band, somewhere between 70 and 170, with the true answer depending on a piece of information, the precise age of an entire stellar nursery, that astronomers are still working to pin down with greater precision. What's just as interesting as the final number is what these objects might be telling researchers about which planets are easiest and hardest to throw out of their home systems in the first place. Miret Roig made a point about this that's worth sitting with. The free-floating Jupiter mass planets being found in surveys like this one are, according to her, actually the hardest type of planet to eject from a system. Jupiter mass planets are big, and big things require a correspondingly large amount of gravitational force to fling out of a system entirely. Which raises an obvious follow-up question. If even the hard-to-eject massive planets are turning up in these numbers, what does that imply about smaller Earth mass planets, which would be considerably easier to kick out by comparison? Miret Roig's own conclusion was direct. There might even be more free-floating Earth mass planets wandering the galaxy, she said, than the Jupiter mass ones currently being detected. The planets we're finding with today's instruments may, in other words, represent the most stubborn, hardest to dislodge fraction of a much larger population, the rest of which remains essentially invisible to current technology, simply because Earth-sized worlds are both smaller and fainter than Jupiter-sized ones, and current detection methods are tuned to catch the bigger, brighter objects first. Bowie, another author on the study, put a number to the bigger picture that the Upper Scorpius discovery was pointing toward. There could be several billions of these free-floating giant planets roaming freely throughout the Milky Way, without a host star, he said, a figure that lines up closely with the broader estimates coming out of the microlensing surveys discussed earlier. Two completely different detection methods, direct imaging in a nearby stellar nursery and statistical microlensing across the wider galaxy, converging on roughly the same conclusion. Rogue planets aren't an edge case. They're a fundamental part of the galaxy's planetary population, present in numbers large enough to genuinely rival, and possibly exceed, the number of stars themselves. The researchers were candid about the limits of what they could say with current technology too. These objects, by their own description, are extremely faint, making them incredibly challenging to find even with today's best telescopes. The team also pointed toward the future, noting that the new Vera C. Rubin Observatory, which would be coming online in the years following the announcement, was expected to push these numbers even higher, finding many more free-floating planets than this single Upper Scorpius survey had managed to catch. The Upper Scorpius discovery also reopened the same fundamental question that had been simmering since the early 2000s. Where do these planets actually come from? Were the 70 to 170 newly identified objects ejected from systems that once orbited stars in this association, flung outward sometime in the past few million years by gravitational chaos among siblings, or did some of them, like OTS 44 decades earlier, simply form on their own from collapsing pockets of gas, never having had a star to begin with? The team noted that both formation pathways likely contribute to the total population, and untangling exactly how much each one contributes remains an open and active area of research. It's a question that wouldn't get its strangest, most theory-challenging answer until astronomers turned their attention, just 2 years later, to one of the most famous stellar nurseries in the sky, using a telescope unlike anything that had come before. That telescope was the James Webb Space Telescope, and the target was the Orion Nebula, also catalogued as Messier 42, a sprawling stellar nursery sitting around 1,350 light-years from Earth. At the end of 2023, 2 astronomers, Samuel Pearson and Mark Makorian, used JUIC's near-infrared camera to study the inner Orion Nebula and the trapezium cluster at the heart of it, an area packed with newly forming stars. The survey covered a region of sky measuring 1.2 by 0.8 parsecs, and the team spent approximately 35 hours gathering observations, using 12 different infrared filters, each one specifically chosen to pick up the molecular absorption features, water and methane in particular, that are characteristic of very low-mass, planet-sized objects. This wasn't a quick glance. It was a deliberate, methodical search, designed from the ground up to catch exactly the kind of faint, isolated bodies that had been turning up elsewhere in smaller numbers for years. What the team found stunned the entire field. Across that single patch of sky, they identified 540 free-floating Jupiter mass objects. 540 in one stellar nursery, in one survey. That number alone would have been a major discovery on its own, since it represented one of the largest single hauls of isolated planetary mass objects ever recorded. But buried within that population was something stranger still, something nobody had been specifically looking for, and that didn't fit cleanly into any existing model of how planets or stars come to be. 40 of those objects weren't alone. They were paired up, locked in mutual orbits around each other, 2 planet-mass bodies circling a shared center of gravity with no star anywhere nearby. The team found 2 additional triple systems on top of that. Pearson and Makorian gave this newly identified class of object a name that stuck almost immediately: Jupiter Mass Binary Objects, or JUMBOs for short. The individual components inside these pairs ranged in mass from about 0.6 to 14 times the mass of Jupiter, and despite existing in pairs, they weren't huddled close together. The typical separation between 2 objects in a JUMBO pair came out to roughly 200 astronomical units, which is about 200 times the distance between Earth and the Sun. Picture 2 Jupiter-sized worlds, each one capable of existing entirely on its own, locked in a slow gravitational dance with each other across a gap 200 times wider than our entire inner solar system, with no star providing the gravitational anchor that normally holds a system like that together. Pearson, who works as a research fellow for the European Space Agency at the European Space Research and Technology Centre in the Netherlands, described what made these objects so visually striking, despite their bizarre nature. Although some of them are more massive than Jupiter, he explained, they would actually be roughly the same physical size as Jupiter, only slightly larger, since gas giant planets don't grow proportionally larger just because they gain more mass. Past a certain point, additional mass actually compresses a gas giant rather than expanding it. Pearson also spoke to just how dependent this discovery was on the specific capabilities of the telescope being used. The objects they were looking at, he said, are really faint, and they're brightest in infrared light, which is exactly where you'd want to be looking if you hope to find them. JUMEST, he pointed out, is the most powerful infrared telescope ever built, and observations like these simply wouldn't have been possible with any previous instrument. The reason JUMBOs caused such a stir in the scientific community goes beyond their sheer number. It's that they shouldn't exist, at least not according to the models astronomers had built up over decades of studying how stars and planets form. The basic problem is one of gravity and scale. Binary star systems, two stars orbiting each other, are common throughout the galaxy, and astronomers understand reasonably well how they form, through the fragmentation of a large collapsing gas cloud into two separate centers of mass, each one massive enough to become its own star. But GMBOs are nowhere near star mass. They sit in the planetary mass range, well below the threshold typically required for that kind of cloud fragmentation process to work cleanly. And yet here they were, paired up at wide separations, in numbers far higher than anyone expected. Research into the binary fraction found that roughly 9% of these isolated objects existed in pairs, a binary rate dramatically higher than what's observed in other substellar objects of similar separation and slightly higher mass. That inconsistency, a binary fraction that goes up rather than down as you move toward lower mass objects, ran directly against a well-established trend in the field, one that had previously suggested multiplicity, the tendency of objects to pair up, should decrease as primary mass decreases. GMBOs broke that pattern outright. Theorists scrambled to explain how something like this could form at all. One proposed explanation suggested these wide planetary mass binaries might be the product of a close stellar flyby, a near collision between two sun-like stars early in their formation, violent enough to strip away planet mass fragments and fling them out together as a bound pair, rather than as two separate, unrelated rogue planets. Other researchers explored a different mechanism entirely, involving the photoerosion of fragmenting molecular cloud cores, essentially the idea that intense radiation from nearby massive young stars in a crowded nebula like Orion could carve smaller cores out of a larger collapsing cloud, cores small enough to end up in the planetary mass range rather than growing into full stars, with some of those cores ending up gravitationally bound to a neighbor in the process. Neither explanation is fully settled, and as of the most recent research, the formation mechanism behind GMBOs remains one of the open puzzles in modern planetary and stellar astrophysics. But there's an even more fundamental controversy sitting underneath all of this theorizing, one that strikes at whether GMBOs are real at all. In 2024, Kevin Luhman, a professor in the Department of Astronomy and Astrophysics at Penn State, went back through the original JST observations and came to a very different conclusion than Pearson and Makorian had. Luhman proposed that the objects identified as GMBOs weren't planetary pairs floating in the Orion Nebula at all, but rather distant background objects, possibly reddened stars sitting far behind the nebula, that had been serendipitously captured in the same field of view and misidentified as nearby, low-mass planetary pairs. A separate reanalysis of earlier, unpublished claims related to this discovery similarly identified background sources, or brown dwarf stars, rather than confirmed GMBO objects. This isn't a small disagreement. It's a direct challenge to whether the entire category of object exists in the way it was first announced, and the scientific community has, as of the most recent published research, not fully resolved the dispute. The matter, according to researchers involved, will likely require follow-up spectroscopy from JST itself to settle definitively, separating the spectral signatures of nearby cold planets from those of distant reddened stars. While that debate has played out, other researchers went looking for independent confirmation using an entirely different kind of instrument, radio telescopes. A team searched the archives of the Carl G. Jansky Very Large Array, a network of radio dishes operated by the National Radio Astronomy Observatory, looking for any radio emission coming from the locations of the proposed GMBOs. Out of all the candidates examined, they found a detection associated with just one object, designated GMBO24, the pair with the largest combined mass in the entire GMBO catalogue at 23 Jupiter masses total, and the closest separation between its two components, just 28 astronomical units apart, considerably tighter than the typical 200 astronomical unit gap seen across the broader sample. The radio signal, detected at frequencies of 6.1 and 10.0 GHz, showed up consistently across three separate observation epochs spanning more than a decade, in 2012, 2018, and again in 2022. Archived data that predated the official GMBO announcement entirely. The emission held steady at a level of about 50 microjanskys, an extremely faint signal, but a real and repeatable one, appearing to come from both components of the pair rather than just one. Crucially, the team found no significant proper motion between the three observation epochs, which ruled out velocities of 15 kilometers per second or greater across the plane of the sky, a finding that's at least consistent with GMBO-24 being a real, physically bound, slowly moving system relatively close to us, rather than a fast-moving or extremely distant background contaminant. That radio detection doesn't settle the broader controversy across all 40 GMBO pairs, but it does offer at least one data point supporting the idea that some of these objects are exactly what they first appeared to be: genuine pairs of planet-mass bodies, born together or captured together, drifting through the Orion Nebula with no star to call their own, defying the models astronomers had relied on for decades to explain how planets and stars come into existence in the first place. Whatever the final verdict turns out to be, the GMBO saga captures something essential about this entire field of study. Every time astronomers think they've found the edge of what's possible, the universe tends to hand them something stranger. As the GMBO controversy unfolded, a separate breakthrough was happening using the older, more established method of gravitational microlensing, and it solved a problem that had limited that technique since the very first rogue planet detections back around the year 2000. For more than 2 decades, microlensing had been excellent at proving rogue planets existed in large numbers, but it had a fundamental blind spot. A single observation of a lensing event from a single vantage point simply doesn't contain enough information to independently calculate both the distance to the lensing object and its mass. Astronomers could say, with confidence, that something planet-sized had passed in front of a background star. They usually couldn't say exactly how far away it was, or exactly how massive it was, not without additional information that microlensing alone doesn't normally provide. That changed on January 1, 2025, when an international team, led by Subo Dong, a professor at Peking University, published a study in the journal Science describing the first rogue planet ever to have both its mass and its distance measured simultaneously and directly. The object, given the catalogue designation KMT 2024 BLG-0792, turned out to be located roughly 9,950 light-years from Earth, off toward the bulge at the center of the Milky Way, and its mass came out to approximately 70 times the mass of Earth, which works out to roughly 22% of Jupiter's mass, putting it in the same general size range as Saturn. The breakthrough came down to a clever bit of cosmic geometry. The research team combined data from several ground-based microlensing surveys with observations from the Gaia Space Telescope, a spacecraft that orbits far from Earth, roughly 930,000 miles out. Because Gaia was sitting at such a different vantage point in space compared to telescopes on Earth's surface, the exact same microlensing event, the same brief brightening of the same background star caused by the same passing rogue planet, appeared slightly differently from each location. Specifically, Gaia recorded the event happening about 2 hours later than ground-based telescopes did. Subo Dong compared the underlying principle to how human depth perception works, with 2 eyes positioned slightly apart, each capturing a marginally different view of the same object, with the brain combining those 2 views to calculate distance. Replace the 2 eyes with a telescope on Earth and a telescope nearly 1 million miles away in space, and that small 2-hour timing difference, known formally as microlensing parallax, becomes enough information to triangulate both the planet's distance and, through additional modeling involving a technique called finite source point lens modeling, its mass as well. This was, by the team's own description, a rare success, the kind of measurement that had been theoretically possible for years, but had never actually come together in practice for a free-floating planet before. Subo Dong summarized what the achievement meant for the field going forward in a simple, direct statement. "The door is open to study this new emerging population of planets," he said. That phrase, "the door is open," captures something important about where this entire area of research stood as of early 2025. For 2.5 decades, astronomers had been gathering indirect evidence, statistical estimates, brightness-based inferences, and ambiguous lensing flickers, slowly building a case that rogue planets were common and important. What had been missing, in almost every case, was the kind of hard, direct, individually verified measurement that planetary science around actual stars had enjoyed for decades. KMT 224 BLG 0792 represented the first time a rogue planet had been pinned down with that same level of confidence, distance and mass both, derived directly from observation rather than statistical inference. The significance of the achievement wasn't lost on researchers outside the immediate study either. Gavin Coleman, a postdoctoral researcher at Queen Mary University of London, who authored a related commentary published alongside the study in Science, but who wasn't directly involved in the research itself, offered an outside perspective on why this particular measurement mattered so much. What's really great about this work, and really noteworthy, is that it's the first time we've got a mass for these objects, Coleman said. He went on to explain exactly why this particular study succeeded, where so many previous attempts had fallen short. This was purely because the authors had both ground-based observations and Gaia, looking at observations from two different places. It's a deceptively simple explanation for what amounts to a major technical achievement. The difference between a guess and a measurement, in this case, came down to literally looking at the same brief flicker of starlight from two different points in space at once, and doing the careful mathematical work to translate that small difference in timing into hard numbers. The discovery also matters for what comes next. Astronomers now have, for the first time, a verified technique for nailing down both distance and mass for free-floating planets discovered through microlensing, rather than relying purely on statistical population estimates drawn from large numbers of ambiguous events. As more space-based observatories come online in the coming years, capable of providing that same parallax-style second vantage point that Gaia provided here, researchers expect to be able to apply this same approach to a growing catalogue of individual rogue planets, building up a much more detailed, much more confident picture of exactly what kinds of objects are out there, one confirmed measurement at a time, rather than one statistical estimate at a time. Just months after that breakthrough, an entirely different kind of rogue planet story emerged, one that had nothing to do with measuring distance or mass, and everything to do with catching one of these isolated worlds in the middle of doing something nobody expected a planet to do at all. That story centered on an object called CHA 1107-7626, a rogue planet sitting about 620 light-years away in the constellation Chamaeleon, with a mass somewhere between 5 and 10 times that of Jupiter. New observations made using the European Southern Observatory's Very Large Telescope, located in Chile's Atacama Desert, revealed that this particular free-floating planet was actively feeding, pulling in gas and dust from a surrounding disk of material at a staggering rate of 6 billion tons per second. That figure is, according to the researchers who made the observation, the strongest growth rate ever recorded for a rogue planet, and remarkably, the strongest growth rate ever recorded for a planet of any kind, including planets that still orbit a star. The lead author of the study, Victor Almendros Abad, an astronomer at the Astronomical Observatory of Palermo in Italy, summed up why this discovery mattered, with a line that cuts right to the heart of what makes rogue planets such a compelling subject in the first place. People may think of planets as quiet and stable worlds, he said, but with this discovery, we see that planetary mass objects freely floating in space can be exciting places. It's a small statement, but it pushes directly against the instinctive image most people probably carry around in their heads of what a rogue planet must be like. Cold, dark, inert. A frozen rock or a dim ball of gas, drifting through emptiness, doing absolutely nothing of interest for billions of years. CHA 1107-7626 is doing the opposite. It is, at this very moment, in the middle of an active, dramatic growth spurt, gaining mass at a rate so extreme that Almendros Abad described it in equally direct terms elsewhere in the study. This is the strongest accretion episode ever recorded for a planetary mass object, he said. The growth wasn't even steady. Researchers tracked the rate of accretion over time and found it had been climbing. By August of 2025, CHA 1107-7626 was pulling in material roughly 8 times faster than it had been just a few months earlier. Something was actively intensifying the planet's feeding process, and the team's investigation pointed toward an unexpected culprit: magnetism. The data suggested that magnetic activity within the young planet appeared to be playing a direct role in driving this dramatic inflow of mass, channeling material from the surrounding disk down onto the planet's surface along magnetic field lines. That kind of magnetically driven accretion has been documented before, but only in stars, not in planets, and certainly not in planets with no star anywhere nearby to influence them. Co-author Belinda Damian, an astronomer at the University of St. Andrews, framed the broader significance of the finding this way. This discovery blurs the line between stars and planets and gives us a sneak peek into the earliest formation periods of rogue planets. There's one more striking detail buried in the data. As researchers compared the chemistry of the disk surrounding CHAR 1107-7626 before and during this intensified accretion episode, they detected water vapor present during the burst that hadn't been there before it started. Water vapor showing up specifically during an episode of intensified accretion has been observed before in disks around young stars, but this marked the first time it had ever been spotted happening around a planet of any kind. The findings, published in the astrophysical journal Letters, paint a picture of CHAR 1107-7626 not as a static, finished object, but as a world still very much under construction, actively pulling in the raw material that will determine its final composition, generating magnetic fields powerful enough to direct that material's fall, and cycling through chemical processes typically reserved for the births of stars, all while having no star of its own anywhere in sight. Taken together with the JWMBO controversy and the precise mass and distance measurement of KMT 2024 BLG 0792, the discovery of an actively accreting rogue planet rounds out a picture that's been building for the past several years. This isn't a settled field where astronomers are simply tallying up a known type of object in ever larger numbers. It's a genuinely active, frequently surprising area of research, where nearly every new observation seems to challenge some previous assumption about where the line between planet, star, and something else entirely is supposed to be drawn. So where does all of this leave the question that's been quietly running underneath everything covered so far? Just how many of these worlds are actually out there? The honest answer, even now, is that nobody knows for certain, but the range that astronomers currently work with is staggering on its own. The Milky Way alone may contain anywhere from billions to trillions of rogue planets, a range so wide it might sound almost like astronomers are simply throwing up their hands, but it actually reflects something more specific: real uncertainty in the underlying data, stacked across multiple independent lines of evidence, all of which point in the same general direction, even as they disagree sharply on the precise scale. Andrzej Udalski, the University of Warsaw astrophysicist whose work has spanned much of this field's development, summarized the theoretical expectation plainly. Planetary system formation models suggest rogue planets should be extremely numerous throughout the Milky Way, he said, potentially even a few times more numerous than the stars themselves. Hervé Bouy, working from the direct imaging side of the field rather than the microlensing side, arrived at a complementary estimate, suggesting there could be several billion free-floating giant planets alone roaming the galaxy without any host star. And the original 2011 SUMI study, even with the later 2017 MROS study revising that figure downward by roughly a factor of 8, still confirmed the basic existence of a Jupiter-mass rogue planet population large enough to be measured statistically across tens of millions of monitored stars. What's coming next promises to finally narrow that enormous range down. NASA's Nancy Grace Roman Space Telescope now carries an official launch date of August 30th, 2026, 8 months ahead of its original schedule. Roman is built specifically to scan enormous swaths of sky with extraordinary precision, and over its first 5 years of operation, it's expected to capture more than 50 times as much sky as the Hubble Space Telescope managed across 3 full decades of operation. Scientists working on the mission expect Roman to help confirm more than 100,000 exoplanets in total, and to spot hundreds of additional planetary systems still in the process of forming. Roman's wide-field infrared survey capability makes it especially well-suited to catching the kind of microlensing events that have driven so much of rogue planet research up to this point. And researchers expect the mission to dramatically increase the rate at which these events are detected, while also, hopefully, enabling more of the kind of parallax-based mass and distance measurements that Subo Dong's team pioneered with KMT 2024 BLG 0792. Roman won't be working alone either. China has its own infrared survey mission planned, an Earth 2.0 satellite scheduled for launch in 2028, designed to complement Roman's search by providing additional sky coverage and observation capability from a different vantage point. And on the ground, the European Southern Observatory's upcoming extremely large telescope, currently under construction in Chile, is expected to help push direct imaging detection capabilities even further, an important development given just how faint these objects are, and how much detection of rogue planets currently depends on catching them at exactly the right moment, with exactly the right combination of sensitivity and timing. Between Roman's wide survey coverage, China's complementary infrared mission, and the extremely large telescope's improved direct imaging sensitivity, the next several years are positioned to deliver more rogue planet detections than the entire previous 25 years of research combined. And with each new detection comes the chance to finally narrow that billions to trillions range down into something far more precise. All of this raises a question that's probably been sitting in the back of your mind since the start of this video. With potentially trillions of these worlds drifting through the galaxy, completely cut off from any source of starlight, is there any chance, however small, that something could actually be alive on one of them? To be clear from the outset, no rogue planet or rogue planet moon with confirmed water, ice, or life has ever actually been found. Everything covered in this next section comes from theoretical modeling and laboratory simulation, not direct observation. Scientists have not detected life, or even direct evidence of liquid water, on any free-floating planet. What they have done is run the numbers on whether it's physically possible, and the results of that work are more interesting than you might expect. The basic problem with a rogue planet is obvious enough. Take away a star, and you take away the single biggest source of energy that life as we understand it relies on. On Earth, more than 99.9% of the energy driving our entire biosphere comes from sunlight, whether that's through plants directly converting it via photosynthesis, or through the sun's warmth keeping our oceans and atmosphere in the temperature range where liquid water and complex chemistry can happen at all. Strip the sun away entirely, and you're left with whatever scraps of energy a planet can generate internally, primarily heat left over from its own formation, and heat generated by the slow radioactive decay of elements buried in its core and mantle. That's an extraordinarily small energy budget compared to what a star provides, and for decades the assumption was that it simply wouldn't be enough to sustain anything resembling liquid water, let alone life. But a 1999 research paper titled "Life-Sustaining Planets in Interstellar Space" challenged that assumption in a specific and physically grounded way. The paper, building on earlier work by a researcher named Stevenson, argued that a sufficiently dense, hydrogen-rich atmosphere could change the entire equation. Under extremely high pressure, hydrogen molecules behave differently than they do in a thin atmosphere like Earth's. When hydrogen molecules collide with each other under that kind of pressure, they can briefly absorb infrared radiation that would otherwise simply radiate away into space, a process called pressure broadening of far-infrared absorption. The practical effect of that process is that a thick hydrogen atmosphere can act almost like an insulating blanket, trapping a planet's modest internal heat far more effectively than a thin atmosphere ever could, potentially keeping enough warmth at the surface to support liquid water using nothing but geothermal heat flux from deep inside the planet, no sunlight required at all. This isn't purely a back-of-the-envelope theoretical claim either. Laboratory experiments simulating hydrogen-rich environments have shown that certain terrestrial microorganisms, organisms that already exist here on Earth, are capable of surviving under exactly those kinds of conditions. That doesn't prove life exists on any actual rogue planet, but it does establish that the basic chemistry involved isn't some exotic, impossible stretch. The kind of environment a hydrogen-blanketed rogue planet might offer isn't necessarily hostile to life as we already understand it, at least not in principle. A more recent and far more detailed study, published in February in the journal Monthly Notices of the Royal Astronomical Society, pushed this same basic idea further, applying it specifically to moons orbiting rogue planets rather than to the planets themselves. The research team behind that study, led by David Dalbuding at Ludwig Maximilian University of Munich, ran simulations looking at what happens to different kinds of atmospheres once a planet and any moons orbiting it get ejected from their original star system out into the cold of interstellar space. Their findings highlighted an important distinction between different atmospheric gases. In the extreme cold of deep space, carbon dioxide, a gas that plays a major role in keeping Earth's own atmosphere warm through the greenhouse effect, actually condenses into a solid or liquid state under those frigid conditions. Once that happens, a carbon dioxide-based atmosphere essentially collapses, falling out of the sky and onto the surface, allowing whatever heat remains underneath to simply radiate away into space unimpeded. Hydrogen, however, behaves in a fundamentally different way under those same cold, high-pressure conditions. Rather than collapsing, a thick hydrogen atmosphere becomes an even more effective insulator the colder and denser its surroundings get, precisely because of that same collision-driven heat absorption described in the earlier 1999 research. The implications of that distinction, according to the simulations, are substantial. Some exomoons orbiting rogue planets in deep interstellar space with the right kind of dense hydrogen atmosphere could theoretically stay warm enough to maintain liquid water and therefore remain potentially habitable for as long as 4.3 billion years. For context, that's not far off from the entire age of life on Earth itself. Dahlböding summarized what this kind of finding means for how scientists think about the basic requirements for life in the universe. Our collaboration with the team of Professor Dieter Braun helped us recognize that the cradle of life does not necessarily require a sun, he said. It's a striking statement, and one that would have sounded almost like science fiction a generation ago. The assumption that a star is a non-negotiable ingredient for a habitable world, baked into how most people instinctively think about the search for life elsewhere in the universe, may simply not hold up once you account for the physics of dense, pressurized hydrogen. Beyond hydrogen-blanketed atmospheres, there's an entirely separate pathway researchers have explored, one that doesn't rely on an atmosphere holding in heat at all, but instead looks underneath the surface entirely. Once a planet gets ejected from its home star system, scientists believe any atmosphere it had would, in most cases, eventually collapse and freeze onto the surface as the planet cools in the absence of starlight. But heat generated by ongoing radioactivity deep within a planet's core doesn't simply disappear once the surface freezes over. That internal heat could, according to multiple studies, be enough to keep a layer of liquid water flowing beneath an insulating cap of surface ice, similar in basic concept to the subsurface oceans already confirmed to exist on several icy moons right here in our own solar system. This specific scenario has its own dedicated name in the scientific literature, the Steppenwolf planet. The term comes directly from the imagery it evokes, a rogue planet harboring a subglacial ocean with any life that might exist in that hidden ocean living, quite literally, like a lone wolf wandering an endless frozen steppe, cut off from everything else, surviving entirely on its own. In this scenario, geothermal heat rising from the planet's interior would be carried upward through the overlying ice layer, partly through simple conduction and partly, in the warmer, less rigid lower portion of that ice, through convection, with the whole system reaching some kind of long-term balance between heat escaping at the top and heat being continually generated at the bottom by ongoing radioactive decay. A subglacial ocean on a Steppenwolf planet could, in principle, serve as a habitat for life that survives not on sunlight or photosynthesis at all, but on chemical energy, drawing on minerals and compounds continually exposed by an active, churning mantle deep below the ice. This isn't just speculation pulled out of thin air either. We already have a working example of exactly this kind of environment right here in our own solar system, just without the rogue planet part. Jupiter's moon Europa and Saturn's moon Enceladus both show strong evidence of thick icy shells sitting over genuine liquid water oceans underneath, kept liquid not by sunlight, since both moons sit far too distant from the sun for that, but by internal heating, largely driven by the gravitational tug-of-war of tidal forces from their much larger host planets. Europa, in particular, is thought to potentially hold roughly twice as much water as exists across all of Earth's oceans combined, locked away beneath its icy crust. And when NASA's Cassini spacecraft flew directly through plumes of water erupting from cracks in Enceladus's icy surface, plumes being vented straight out of that moon's subsurface ocean, it detected organic molecules the basic chemical building blocks associated with life present in that ejected material. Follow-up analysis of that data suggested Enceladus's hidden ocean may even contain active hydrothermal vents, similar in basic structure to the ones found in the deepest, darkest parts of Earth's own oceans. Environments here on Earth where entire ecosystems of microorganisms, including a group called methanogens, thrive in complete darkness, relying entirely on chemical and thermal energy rather than sunlight to survive. If a moon like Europa or Enceladus can sustain a potentially habitable subsurface ocean while still orbiting a planet that itself orbits the Sun, the obvious next question is what happens if you take that same icy moon and eject the entire system, planet, moon, and all, out into the cold of interstellar space. Researchers studying this exact scenario have pointed out that a rogue planet doesn't necessarily need to support life entirely on its own internal heat if it happens to have a large moon orbiting it. A sufficiently massive moon, locked into a tight orbit around a rogue planet, would continue generating tidal heating through the same basic gravitational flexing that keeps Europa and Enceladus's interiors warm today, an entirely separate heat source from the planet's own radioactive decay, and one that doesn't depend on starlight in any way at all. There's even a useful, much closer to home example of how powerful this kind of tidal heating can be early in a system's history. When Earth's own moon first formed, more than 4.4 billion years ago, it sat roughly 15 times closer to Earth than it does today, and the resulting tidal forces between the two bodies were intense. Intense enough that some scientists believe that early tidal heating may have played a meaningful role in making the young Earth habitable in the first place. Apply that same basic mechanism to a large moon orbiting an ejected rogue planet, drifting through interstellar space with no sun anywhere nearby, and you get a plausible, physically grounded pathway towards sustained internal warmth, entirely independent of starlight. Researchers studying the broader astrobiological potential of these worlds have laid out the basic categories involved. There are, broadly speaking, two different types of rogue planets worth distinguishing here. Sub-brown dwarfs, the more massive class of free-floating objects that sit closer to the boundary separating planets from failed stars, are considered unlikely candidates for hosting life under any of these scenarios. But the second category, smaller, rocky rogue planets, are the ones where these various heating mechanisms, dense hydrogen atmospheres, subglacial oceans warmed by radioactive decay, or tidal heating from a large orbiting moon, become genuinely relevant. Given how difficult these rocky rogue planets already are to detect in the first place, researchers are upfront about the fact that there is currently no direct evidence of water or ice existing on any of them. Everything remains theoretical, grounded in physics and chemistry that researchers have high confidence in, but entirely unconfirmed by direct observation. There's also a question of just how common the basic ingredients for this scenario might be in the first place. Researchers Manasvi Lingam, an assistant professor at Florida Tech specializing in astrobiology, and Avi Loeb, a prolific researcher in the same field, examined planets with subsurface oceans specifically, and estimated that such planets could be somewhere between 100 and 1,000 times more common throughout the galaxy than rocky planets sitting in the traditional habitable zone around a star, the classic, sun-warmed sweet spot most discussions of alien life tend to focus on. If even a modest fraction of those subsurface ocean planets eventually get ejected from their home systems and become rogue planets themselves, carrying their hidden oceans with them out into interstellar space, the sheer scale of potential habitats hiding beneath the ice across the galaxy starts to look considerably larger than the relatively narrow band of traditionally habitable, sun-orbiting worlds that most searches for extraterrestrial life have historically focused on. Lingam's broader research has also examined some of the practical challenges any life on a rogue planet's subsurface ocean would actually face, even assuming the basic energy and chemistry requirements are met. One issue involves radiation. Lingam's work found there's a delicate balance between visible light being potentially useful for some form of photosynthesis in shallower portions of a subsurface ocean and the harmful effects of extreme ultraviolet radiation on living cells. The good news, from a habitability standpoint, is that even a relatively modest barrier, a layer of soil or the first few meters of ocean water itself, can effectively shield deeper life from that harmful ultraviolet radiation, while still allowing enough usable visible light through to support some form of photosynthetic activity, at least in theory. Lingham's research has even examined more exotic energy sources, suggesting that for a rogue planet located close enough to an active galactic nucleus, the supermassive black hole and surrounding high-energy environment found at the center of certain galaxies, that nucleus might provide enough radiation to support life on a rogue planet within roughly 1,000 light-years of the galactic center. For context, Earth itself sits about 25,000 light-years from the center of the Milky Way, a useful reminder of just how specific and limited that particular scenario would actually be. There's one more genuinely strange wrinkle in all of this research worth mentioning. Some scientists studying rogue planets have gone a step further than simply asking whether life could survive on one, and have started asking whether rogue planets could actually help spread life between star systems entirely. The basic idea, sometimes discussed under the broader term panspermia, the transfer of life or its chemical building blocks from one location to another, suggests that a rogue planet, drifting slowly through the galaxy over enormous timescales, carrying a hidden subsurface ocean and whatever microbial life might exist within it, could theoretically pass close enough to other star systems over its long journey to potentially seed or contribute material to other worlds. This remains highly speculative, sitting right at the edge of what current science can meaningfully evaluate, but it captures something compelling about how scientists are beginning to think about these objects. A rogue planet isn't necessarily just a dead end, a frozen, isolated world doomed to drift alone forever with nothing happening on it. It might, under the right circumstances, be something closer to a vessel, slowly carrying whatever chemistry or biology it holds across vast stretches of the galaxy, completely independent of any star's gravity or light, on a journey with no fixed destination and no end in sight. It's worth being honest about where the science actually stands on all of this, though, before getting too carried away with the more dramatic possibilities. Every mechanism described here, the hydrogen blanket atmosphere, the tidally heated exomoon, the Steppenwolf subglacial ocean, the panspermia hypothesis, represents a genuinely serious area of scientific modeling, published in peer-reviewed journals, grounded in real physics and chemistry, that researchers have tested and have reasonable confidence in. But none of it amounts to confirmed detection. Nobody has found water on a rogue planet. Nobody has detected a biosignature, any kind of chemical fingerprint suggestive of life, on a free-floating world or its moon. What exists right now is a strong, physically plausible case that the conditions for life don't strictly require a star, paired with an almost complete absence of direct observational evidence, either confirming or ruling that possibility out. Closing that gap, turning theoretical plausibility into an actual detection, is likely to depend heavily on exactly the kind of next-generation instruments discussed earlier. Instruments capable of finding far more rogue planets than currently exist in the catalogue, and eventually, perhaps, capable of characterizing their atmospheres and surfaces in enough detail to actually test these hypotheses directly, rather than simply theorizing about them from a distance. Given everything covered so far, the possibility of billions, maybe trillions, of unseen planet-sized objects drifting through the galaxy, it's a reasonable question to ask whether any of this poses an actual threat to us. Could a rogue planet drift into our solar system? Could one collide with Earth, or knock our planet out of its own stable orbit? The short answer, according to researchers who've actually run the numbers, is no, not in any time frame that should concern anyone. Cassidy Ward, a professor specializing in celestial mechanics, has put a specific figure on just how unlikely this scenario actually is. The odds of a rogue planet entering our solar system within the next 1,000 years, according to Ward's estimate, come out to roughly 1 in a billion. And even setting that already remote possibility aside, the odds of a rogue planet posing any kind of direct threat to life on Earth specifically are described as vanishingly small. It helps to understand why those odds are so low, given how many of these objects are theorized to exist. The galaxy is, despite containing potentially trillions of rogue planets, still almost entirely empty space. Stars themselves, even with roughly 100 billion of them scattered across the Milky Way, are separated from each other by distances so vast that meaningful collisions or close encounters between star systems are exceptionally rare events on any human timescale. Rogue planets, drifting individually through that same vast emptiness, are even less likely to intersect with any particular star system, including ours, simply because of how much open space there is for them to be moving through. A rogue planet would need to be heading directly toward our solar system, on a trajectory that happens to bring it close enough to interact gravitationally with the Sun or its planets, out of the literally countless possible directions and paths available to it across the galaxy. The math simply doesn't favor that happening, not within any time frame remotely relevant to human history, or even to the much longer span of life's history on Earth. So while rogue planets are out there in genuinely staggering numbers, and while it's entirely possible that some of them have, over the roughly 4.5 billion years our solar system has existed, drifted reasonably close to us at some point in the deep past, there's no credible scientific basis for treating them as any kind of looming threat. They remain exactly what they've been throughout this entire story: distant, isolated, almost entirely undetectable objects, drifting through interstellar space on their own paths, with our solar system being just one of an astronomical number of things they could, statistically, never come anywhere near. Step back from the individual discoveries for a moment, the specific catalog numbers and light-year distances and Jupiter mass ratios, and consider what the existence of rogue planets actually does to our basic understanding of what a planet even is. For most of human history, and even for most of the history of modern astronomy, the definition was simple enough that nobody really had to think about it. A planet orbits a star. That was the whole idea. It's baked into the very word itself, which traces back to an ancient Greek term essentially meaning wanderer, originally used to describe the handful of bright objects in the night sky that moved against the fixed backdrop of stars, precisely because they were orbiting our sun and we were watching that orbit play out from our own moving vantage point on Earth. Rogue planets break that definition cleanly in half. Here are objects with all the basic physical characteristics of planets: gas giants like the JUMBO components and PSO J318.5-22. Smaller rocky bodies theorized to exist in even greater numbers. Objects with disks of accreting material around them, like OTS-44 and CHAR 1107-7626. Objects that form through processes recognizably similar to how planets form around stars, and yet none of them have a star. None of them orbit anything at all. They simply exist, moving through the galaxy on whatever trajectory they happen to end up on, whether that trajectory came from being violently ejected out of a system that once had a star, or from forming independently from the start, with no star ever involved in the first place. This forces astronomers into an uncomfortable, but ultimately productive question. What actually makes something a planet, if not the act of orbiting a star? The current working answer, reflected in terms like isolated planetary mass object, focuses on mass and composition rather than orbital relationship. If an object falls below the roughly 13 Jupiter mass threshold where nuclear fusion of deuterium would begin, the threshold separating planets from the smallest brown dwarfs and sub-brown dwarfs, and if it formed through processes recognizably similar to planet formation rather than star formation, then it gets classified as planet-like, regardless of whether anything stellar is anywhere nearby. It's a definition based on what an object is, rather than what it's doing or where it happens to be located, and it represents a genuine shift in how the field approaches the basic question of categorization. This shift matters beyond just academic taxonomy too, because it reshapes how astronomers think about the entire process of how solar systems come into being in the first place. For a long time, the dominant mental image of planet formation was relatively orderly. A young star forms at the center of a collapsing cloud of gas and dust. A flattened disk of leftover material spins around it, and over time, that disk material clumps together into progressively larger bodies, eventually forming a stable, settled system of planets locked into orbits that, barring some catastrophic event, will persist essentially unchanged for billions of years. Our own solar system, with its 8 planets quietly circling the Sun in tidy, well-behaved orbits, fits that orderly picture reasonably well, at least as we observe it today. But the existence of rogue planets, in the staggering numbers suggested by the research covered throughout this video, tells a far messier story about how that process actually plays out across the galaxy as a whole. If Jupiter-mass rogue planets genuinely outnumber stars, or come even close to it. That means the process of building a planetary system isn't nearly as clean or as stable as our own solar system's current quiet state might suggest. It means that for every planet that ends up settled into a long-term, stable orbit around its star, there may be another planet, sometimes more than one, that got caught up in gravitational chaos at some earlier point in that same system's history and was flung outward with enough force to escape entirely, joining the ranks of the galaxy's free-floating population. Nuria Miret-Roig's observation that Jupiter-mass planets are actually the hardest to eject, and that smaller, Earth-mass planets are likely even more common among the rogue population, only deepens this picture. If even the most gravitationally stubborn planets are getting ejected in large numbers, the implication is that smaller, rockier worlds, the kind most similar in size to Earth itself, may be getting kicked out of their home systems even more frequently. That's a genuinely sobering thought to sit with for a moment. Our own solar system has, as far as we currently know, never lost a planet this way. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all appear to have settled into stable orbits relatively early in the solar system's roughly 4.5 billion-year history, and they've stayed there ever since, with no evidence of any additional planet having once existed and later been ejected. But our solar system's quiet stability might be closer to the exception than the rule. Across the wider galaxy, the process of building a planetary system may routinely, perhaps even typically, involve violently casting off one or more planets along the way, almost as a natural byproduct of how gravity sorts out a young, crowded system of newly formed worlds jostling for stable, long-term orbits. The JWMBO discovery complicates this picture even further, assuming the objects hold up against Kevin Luhman's challenge to their existence. If genuine planet-mass binary pairs really are forming, or being captured, in significant numbers within a dense, chaotic stellar nursery like the Orion Nebula, that points toward an entirely separate formation pathway that doesn't fit neatly into either the traditional star and disk model or the simple ejection model. It suggests that in sufficiently crowded, sufficiently violent early environments, the rules governing how gravity sorts mass into stable, bound systems may simply work differently than they do in calmer, more isolated star-forming regions. Untangling exactly how and why that happens remains one of the genuinely open frontiers in this entire field, a frontier that's likely to remain active and contested for years to come, regardless of how the specific jumbo debate eventually resolves. There's also something worth noting about how each new discovery covered in this video built directly on the methods and infrastructure of the discoveries that came before it. The 2011 SUMI study relied on years of patient, continuous microlensing monitoring using ground-based telescopes built specifically for that kind of survey work. The 2013 discovery of PSO J318.5-22 came out of a search that was originally looking for something else entirely, brown dwarfs, and only found a rogue planet because the team was thorough enough to follow up on an unusual outlier in their data. The 2021 Upper Scorpius discovery combined 2 decades of archived images with newly available Gaia satellite data that simply didn't exist yet when the earlier microlensing surveys were being conducted. The 2023 JWMBO discovery required the James Webb Space Telescope, an instrument with infrared sensitivity that didn't exist in any previous generation of telescope, to even attempt the kind of survey that revealed those objects in the first place. And the 2025 KMT 2024 BLG G0792 mass measurement depended specifically on having Gaia in orbit at the same time. Ground-based surveys were running, a combination of circumstances that simply wasn't available to the researchers working back in 2000, when this entire field was just getting started with its first uncertain detections. Each generation of instruments has revealed not just new individual objects, but entirely new categories and behaviors that the previous generation of instruments couldn't have detected even in principle. Direct imaging found OTS-44 and PSO J318.5-22, planets young and warm enough to glow faintly on their own. Statistical microlensing surveys found evidence for an entire hidden population too faint and too cold for any imaging survey to catch directly. Combining archival imaging with space-based positional data turned up 70 to 170 planets clustered together in a single stellar nursery. The unprecedented infrared sensitivity of JUST turned up 540 objects in a single survey of Orion, including an entirely unexpected new class of paired planetary objects nobody had previously theorized in any detail. And the simple, clever trick of combining a ground-based telescope with a space-based one, separated by nearly 1 million miles, finally cracked open the ability to measure a rogue planet's mass and distance directly, rather than simply inferring its existence statistically. If that pattern holds, and there's no obvious reason to think it won't, then the Nancy Grace Roman Space Telescope, China's planned Earth 2.0 mission, and the extremely large telescope currently under construction in Chile aren't just going to add more entries to the existing catalogue of known rogue planets. Based on the history laid out across this entire video, it's reasonable to expect these new instruments will reveal entirely new categories of behavior and structure among these objects. The kinds of discoveries nobody currently has the data to even theorize about yet. The same way nobody fully anticipated JUMBOs before JUST actually went looking, and nobody had a confirmed mass and distance measurement for any rogue planet before Subo Dong's team figured out how to use Gaia's distant vantage point to triangulate one directly. It's worth laying the whole timeline out in order, start to finish, because seeing it all in sequence really does drive home just how quickly this field has accelerated. In the year 2000, astronomers picked up the first faint hints that planet-sized objects might exist without any star nearby, a discovery strange enough to raise questions, but not yet substantial enough to reshape the field. Sometime after that, observations of OTS-44 using the Herschel Space Observatory and the Very Large Telescope confirmed that a young, isolated, planet-sized object could host an actively accreting disk of material. The same basic process seen around forming stars, just with no star involved at all. In 2011, Takahiro Sumi and his colleagues, watching 50 million stars across years of microlensing observations from telescopes in New Zealand and Chile, calculated that there could be nearly 2 Jupiter-mass rogue planets for every star in the Milky Way, a number that, if it held up, implied a population in the hundreds of billions just among Jupiter-sized objects. In October of 2013, Michael Liu's team announced PSO J318.5-22, a young 6 Jupiter-mass planet just 80 light-years from Earth, the first rogue planet famous enough to capture genuine public attention, later refined in 2016, with updated measurements placing its mass closer to 8.3 Jupiter masses. In 2017, Przemek Mróz and colleagues, working with 6 times the statistical data available to the 2011 study, revised the Jupiter mass rogue planet estimate down to an upper limit of about 1/4 of a planet per star, a substantial downward correction that nonetheless still confirmed a real, measurable population. In September of 2020, microlensing surveys detected the first Earth mass rogue planet ever found, designated Ogle 2016 BLG-1928, proving that this phenomenon wasn't limited to large gas giants, but extended down to planets roughly the size of our own. In December of 2021, Nuria Miret-Roig and Hervé Bouilly's team, combining 20 years of Canada-France-Hawaii telescope archives with Gaia satellite data, announced somewhere between 70 and 170 newly discovered rogue planets clustered in the Upper Scorpius Stellar Association, nearly doubling the entire known population in a single announcement. At the end of 2023, Samuel Pearson and Mark Makorian's James Webb Space Telescope survey of the Orion Nebula uncovered 540 free-floating Jupiter-mass objects in a single patch of sky, including 40 unexpected pairs and 2 triple systems, the objects that came to be known as JUMBOs, a discovery so far outside existing theoretical models that it remains genuinely contested within the field, with Kevin Luhman's 2024 reanalysis proposing the objects might actually be distant background stars rather than nearby planetary pairs at all, a controversy that radio observations of JUMBO 24 have only partially addressed. On January 1, 2025, Subo Dong's international team published the first simultaneous mass and distance measurement ever made for a rogue planet, using Gaia's distant vantage point alongside ground-based surveys to triangulate KMT 2024 BLG 0792, a Saturn mass object roughly 9,950 light-years away. And sometime after that, in 2025, the European Southern Observatory's Very Large Telescope caught CHA 1107-7626 in the middle of the most extreme accretion event ever recorded for any planet, gas giant or otherwise, pulling in 6 billion tons of material every second, with magnetic activity and water vapor signatures previously only ever seen around forming stars. Lay that timeline out, and a pattern becomes obvious. 25 years, from a single uncertain hint in 2000 to a directly measured mass and distance in 2025, and the pace of discovery has only been accelerating, not slowing down, as each new generation of instruments comes online. What started as scattered, ambiguous detections that could just as easily have been dismissed as instrumental noise or misidentified brown dwarfs has become, over the course of roughly a quarter century, an entire established subfield of astronomy, with its own dedicated detection techniques, its own ongoing scientific controversies, its own emerging subcategories of object, and its own upcoming generation of purpose-built instruments, designed specifically to push the population estimates from a frustratingly wide range of billions to trillions down towards something far more precise. And underneath all of that accelerating technical progress sits a genuinely strange, almost philosophical fact that's easy to lose sight of amid all the catalog numbers and mass estimates. Every planet most of us grew up learning about, every planet depicted in every textbook diagram of the solar system, orbits something, has a sun, has a sky that brightens and dims on some kind of regular cycle. The planets discussed throughout this entire video have none of that. No sunrise, no sunset, no seasons, no years in any meaningful sense, since a year is fundamentally defined by completing an orbit around a star, and these worlds aren't orbiting anything at all. Whatever light might fall on the surface of a rogue planet comes from the same source available to every other point in interstellar space: the combined, extraordinarily faint glow of distant starlight scattered across the entire sky, supplemented, in the rare cases discussed here, by whatever residual warmth the planet itself still carries from its own birth, slowly leaking away into the surrounding darkness, year after year, with absolutely nothing nearby to replenish it. Even with everything covered in this video, it's worth being honest about how much remains genuinely unresolved. The gap between the 2011 SUMI estimate and the 2017 MROS estimate, nearly an 8-fold difference in how many Jupiter-mass rogue planets exist per star, hasn't been definitively closed. Both studies used real data and real statistical methods, and the disagreement between them reflects the fundamental difficulty of converting a relatively small number of brief, ambiguous microlensing events into a confident population estimate for the entire galaxy. Future surveys, particularly the much larger dataset expected from the Nancy Grace Roman Space Telescope, should help narrow that gap. But as of right now, the honest answer to how many Jupiter-mass rogue planets are there remains a range spanning nearly an order of magnitude. The JWMBO controversy remains similarly unsettled. Samuel Pearson and Mark Makorian's original 2023 announcement described 40 pairs and 2 triple systems of genuine, nearby, planet-mass objects, a finding that directly challenged existing models of star and planet formation. Kevin Luhman's 2024 reanalysis proposed instead that these objects might be distant background stars, misidentified due to their similar appearance in JWST's infrared imaging. The radio detection of JWMBO 24, with its steady emission across 3 separate observation epochs and its lack of significant proper motion, offers at least some support for the idea that this particular object, at minimum, is a real, relatively nearby, slowly moving system. But that single data point doesn't resolve the status of the other 39 candidate pairs, and researchers in the field have indicated that definitive resolution will likely require additional JWST spectroscopy, capable of distinguishing the specific chemical signatures of cold, nearby planets from those of distant, reddened background stars. A follow-up observation that, as of the most recent published research, hadn't yet fully settled the question one way or the other. The question of rogue planet formation, whether most of these objects were ejected from systems that once had stars, or whether a meaningful fraction formed entirely on their own from collapsing pockets of gas, also remains open across the population as a whole. Individual objects offer hints in both directions. OTS-44's actively accreting disk suggests processes consistent with either pathway. The JWMBO pairs, if they're confirmed to be real, point toward formation mechanisms, whether stellar flyby ejection or photoerosion of fragmenting cloud cores, that don't map cleanly onto either the traditional ejection model or the traditional independent formation model. Untangling the relative contribution of each pathway across the broader rogue planet population is likely to remain an active area of research for years, particularly as larger, more statistically robust samples of confirmed rogue planets become available through upcoming surveys. And the habitability question, while grounded in serious, peer-reviewed physics and chemistry, remains entirely theoretical at the observational level. Nobody has detected liquid water on a rogue planet. Nobody has detected a biosignature on a free-floating world or its moon. The hydrogen blanket atmosphere models, the Steppenwolf subglacial ocean concept, the tidally heated exomoon simulations showing potential habitability lasting up to 4.3 billion years, all of it represents serious scientific modeling grounded in well-understood physics, but none of it has yet been tested against an actual observed rogue planet with the kind of detailed atmospheric or surface characterization that would be needed to move these ideas from plausible theory to confirmed reality. What ties all of this uncertainty together, though, isn't a sense that the field is somehow stuck or unproductive. It's closer to the opposite. Every one of these open questions exists precisely because the field has moved fast enough and the available technology has improved quickly enough that new data keeps arriving faster than it can be fully reconciled with everything that came before it. That's not a weakness in the science. That's what an actively developing field of astronomy actually looks like from the inside, full of genuine, productive disagreement, competing interpretations of the same data, and a steady stream of new instruments specifically designed to settle exactly the kinds of disputes currently still open. It's worth taking a moment to really sit with the distances and numbers involved here, because it's easy to let figures like 80 light-years, or 9,950 light-years, or 6 billion tons a second wash over you without actually registering their scale. PSO J318.5-22, at 80 light-years away, is one of the closest rogue planets ever found, and even that counts as practically next door, only because everything else in this story is so much farther away. The Orion Nebula, home to the 540 free-floating objects and the controversial JWMBO pairs, sits 1,350 light-years from Earth, meaning the light reaching JOST's cameras when it captured those objects left them well over 1,000 years before any of the astronomers analyzing that data were even born. KMT 2024 BLG 0792. The rogue planet with the first directly measured mass and distance sits roughly 9,950 light-years away, deep toward the bulge at the center of our own galaxy, a distance so vast that even at the speed of light, the journey from that planet to Earth would take nearly 10,000 years. And these are all relatively local examples, all still within our own Milky Way galaxy, a single galaxy among, by most current estimates, hundreds of billions of others scattered across the observable universe. If the population estimates discussed throughout this video hold up, with rogue planets numbering anywhere from billions to trillions within the Milky Way alone, then the true number of rogue planets across the entire universe becomes a figure that essentially stops being meaningful to humans in any intuitive sense. It's less a number you can picture and more a number you simply have to accept, the same way you accept the existence of numbers like a Google without ever being able to genuinely visualize a quantity that large. The 6 billion tons per second of material falling onto Char 1107 7-26 deserves its own moment of consideration too. 6 billion tons is roughly comparable to the combined mass of millions of large cargo ships falling onto a single planet every single second, continuously, for months at a time, with the rate itself climbing eightfold between early 2025 and August of that same year. That's not a one-time event. That's an ongoing process, happening right now, on a planet with no star, no system, nothing around it except a disk of leftover material that it's slowly, violently consuming. Compare any of this to our own solar system's quiet stability. 8 planets, settled into their orbits for roughly 4.5 billion years. No ejections, no dramatic accretion bursts, No binary planet pairs locked in mutual orbit 200 times wider than the distance from Earth to the Sun, and the contrast becomes genuinely striking. Our solar system, the only one any of us has ever directly experienced, the one that produced every form of life we know to exist anywhere in the universe, might actually represent something closer to an unusually calm, unusually fortunate outcome, rather than the typical, expected result of how planetary systems generally turn out. If Nuria Miret-Roig's reasoning holds, and Jupiter mass planets really are the hardest type of planet to eject from a system, with smaller, Earth mass worlds being ejected even more readily, then the fact that all 8 of our solar system's planets, including Earth itself, remained safely in their orbits across 4.5 billion years of cosmic history starts to look less like the default outcome of planet formation, and more like something closer to a quiet, fortunate exception to a much messier galactic norm. It also helps to understand where rogue planets actually sit on the broader spectrum of objects that fill the space between true planets and true stars, because that spectrum turns out to be far less tidy than most people probably assume. At the low end, you have planets like Earth, rocky, modest in mass, completely incapable of any kind of nuclear fusion under any circumstances. Move up in mass, and you eventually reach gas giants like Jupiter, still firmly planetary, still incapable of fusion, but massive enough to hold on to thick atmospheres of hydrogen and helium. Keep adding mass beyond that, and you eventually cross the roughly 13 Jupiter mass threshold discussed earlier, the point at which deuterium fusion becomes possible, a weak, short-lived form of nuclear burning that nonetheless marks the formal boundary separating planets from brown dwarfs in most current astronomical classification schemes. Brown dwarfs themselves span a fairly wide range above that threshold, objects too small to ever ignite the much more demanding hydrogen fusion that powers a true star, but large enough to generate at least some nuclear energy through deuterium burning, at least for a relatively brief period early in their existence. Keep adding mass further still, somewhere in the neighborhood of roughly 80 times the mass of Jupiter, and you finally cross into true stellar territory, objects massive enough to sustain genuine, long-term hydrogen fusion in their core, the same basic process that powers our own Sun. What makes this spectrum so relevant to the rogue planet story is how many of the objects covered throughout this video sit right at the messy, contested boundary between these categories. The JUMBO components, with masses ranging from 0.6 to 14 Jupiter masses, straddle the planet and brown dwarf line directly, with some individual components sitting clearly within planetary territory and others sitting right at, or just above, the deuterium fusion threshold that would technically classify them as the smallest possible brown dwarfs, rather than true planets. CHAR 1107-7626, at 5 to 10 Jupiter masses, sits safely within planetary territory by mass, but its observed behavior, magnetically driven accretion bursts, and water vapor signatures previously only documented around forming stars, blurs the behavioral line between planet and star in a way that has nothing to do with its actual mass classification at all. And even CHAR 110913, one of the very earliest rogue planet candidates discussed near the beginning of this video, remains genuinely ambiguous between the sub-brown dwarf and ejected planet categories, a classification problem that has never been fully resolved. This kind of boundary blurring isn't a flaw in how astronomers think about these objects. It's a fairly direct reflection of how nature actually works. Mass doesn't come pre-sorted into neat, discrete categories with clean dividing lines between them. It exists along a continuous spectrum, and human classification systems, useful as they are for organizing research and communicating findings clearly, are ultimately just convenient lines drawn across that continuous spectrum at points that happen to correspond to genuine physical transitions, like the onset of deuterium fusion or the onset of hydrogen fusion. Objects that happen to sit right at one of those transition points, as a meaningful fraction of the rogue planets and brown dwarfs discussed throughout this video clearly do, will always generate exactly the kind of classification debates and ongoing scientific disagreement that have run through so much of this story, from the early ambiguity surrounding CHAR 110913 to the JUMBO controversy over whether those objects are real, nearby planetary pairs, or distant background stars, to the broader, still unresolved question of how many of the galaxy's free-floating objects are genuinely planetary in nature, and how many would more accurately be classified as the very smallest, dimmest members of the brown dwarf family instead. The search for life beyond Earth. That search, going back to pioneers in the field, has traditionally focused almost entirely on planets orbiting within a star's so-called habitable zone, the relatively narrow band of distance from a star where temperatures allow liquid water to exist on a planet's surface without either boiling away or freezing solid. Earth obviously sits within our own sun's habitable zone, and for most of the history of the search for extraterrestrial life, finding more planets in that same kind of zone around other stars has been treated as the primary, almost exclusive strategy for narrowing down where else in the universe life might exist. The research into rogue planet habitability covered throughout this video complicates that picture considerably, in a way that's genuinely productive for the field as a whole, even though none of it has yet produced a confirmed detection. If Lingham and Loeb's estimate holds up, that subsurface ocean planets could be 100 to 1,000 times more common throughout the galaxy than traditionally habitable, sun-orbiting rocky planets. And if even a modest fraction of those subsurface ocean worlds eventually become rogue planets through ejection, carrying their hidden oceans out into interstellar space with them, then the total number of potentially habitable environments scattered across the galaxy could be dramatically larger than estimates, based purely on traditional habitable zone calculations around stars would suggest. That doesn't mean any of these environments actually host life. It means the search for life might need to expand well beyond simply counting planets in the right orbital position around the right kind of star, to also account for an entirely separate category of potentially habitable world that doesn't orbit anything at all, and that current search strategies, built around detecting starlight reflecting off a planet or dimming as a planet transits its star, aren't well equipped to find in the first place. This is part of why the upcoming generation of instruments matters so much for more than just expanding the basic catalogue of known rogue planets. If Roman, the extremely large telescope, and China's Earth 2.0 mission do manage to push detection capabilities down toward older, colder, fainter rogue planets, the kind that have remained essentially invisible throughout the first 25 years of this field, and if follow-up instruments eventually develop the sensitivity needed to characterize atmospheres or surface conditions on individual rogue planets, the way astronomers can already do for some planets orbiting nearby stars, the theoretical habitability models discussed earlier, the hydrogen blanket atmospheres, the Steppenwolf subglacial oceans, the tidally heated exomoons, would finally have a real chance of being tested against actual observational data, rather than remaining confined to physics simulations and laboratory experiments, using terrestrial microorganisms as a rough stand-in for what might be possible elsewhere, grounded strictly in what the research already covered tells us, rather than in pure imagination. There would be no sunrise, because there is no sun, and therefore no day-night cycle in any conventional sense at all. Whatever light reached the surface would come from the same diffuse, extraordinarily faint background available everywhere in interstellar space, the combined glow of countless distant stars scattered across the entire sky, none of them close enough or bright enough to function as anything resembling daylight. For a young rogue planet like PSO J318.5-22, still warm with 12 million years of residual formation heat, there would at least be some internal glow, the planet's own infrared warmth radiating faintly outward in every direction, the kind of glow that let Michael Liu's team detect it from 80 light-years away in the first place. For an older, long-since-cooled rogue planet, there might be nothing at all, no internal light, no external warmth, just the slow, steady, almost imperceptible drift through the dark, governed by gravity and momentum, and nothing else. Temperature on a planet like this would depend entirely on internal sources, since there's no external star contributing any meaningful warmth at all. That's precisely the gap that researchers like Stevenson and the team behind the 1999 hydrogen atmosphere paper were trying to close, by asking whether a sufficiently dense atmosphere could trap what little internal heat a planet actually has. The same basic heat budget driven by leftover formation warmth and ongoing radioactive decay deep in the core, efficiently enough to keep liquid water flowing somewhere on or beneath the surface. Without that kind of atmospheric insulation, the surface of a typical rogue planet would likely sit at temperatures closer to the background temperature of interstellar space itself, a few degrees above absolute zero, cold enough to freeze essentially every common substance solid, including, eventually, whatever atmosphere the planet originally had, the same basic collapse process described in the exomoon research discussed earlier, where even carbon dioxide eventually condenses and falls out of the sky entirely under those kinds of extreme conditions. And then there's the matter of time itself, or rather, the absence of any of the usual ways we measure it. A year, as a concept, depends entirely on completing an orbit around a star. Take the star away, and the very idea of a year stops applying in any meaningful sense. A rogue planet doesn't have a year. It has only the passage of time itself, measured in nothing but the planet's own internal clock, whatever that might mean for a world that isn't going anywhere in particular, isn't completing any kind of cycle, and isn't marking the passage of seasons against any external reference point at all. It simply exists, moving in whatever direction its momentum and the galaxy's gravity happen to carry it, for as long as it continues to exist, with no internal or external event marking the start or end of any particular unit of time, the way a sunrise, a season, or a completed orbit would on a planet like Earth. Before wrapping up, it's worth going back to that 13 Jupiter mass boundary mentioned earlier, because it sits at the center of so much of the uncertainty running through this entire field. That number isn't arbitrary. It marks the rough point at which an object becomes massive enough for deuterium fusion to ignite in its core, a much weaker form of nuclear fusion than the hydrogen fusion that powers true stars, but a real nuclear process nonetheless. Cross that threshold, and an object stops behaving purely like a planet and starts behaving, at least a little, like a very small, very dim star. That's the line that separates planets and sub-brown dwarfs from the smallest true brown dwarfs. And it's the exact line that made the Upper Scorpius discovery's final count so uncertain. The line that determines whether a given faint object in Miret-Roig and Buoy's survey counts toward the 70 figure, the 170 figure, or somewhere in between, depending entirely on how old that particular patch of sky actually turns out to be. This boundary also explains something important about why direct imaging and microlensing, the two core detection methods running through this entire story, tend to find such different kinds of objects, and why combining them has proven so valuable. Direct imaging is fundamentally a brightness-based method. It can only find objects that are still warm enough, and therefore young enough, to glow detectably in infrared light, which is exactly why OTS-44 and PSO J318.5-22 were both found to be extremely young, just a few million to 12 million years old, essentially still in their planetary infancy. An older rogue planet, having had hundreds of millions or billions of years to cool, would likely be far too dim for any current direct imaging survey to pick up at all, no matter how close it happened to be to Earth. Microlensing, on the other hand, doesn't care at all about an object's temperature or brightness. It only cares about mass and the geometry of a chance alignment between the rogue planet, a background star, and Earth. That's precisely why microlensing surveys, going all the way back to Sumi's 2011 study, have been able to detect planets regardless of their age, catching old, cold, completely dark rogue planets just as easily as young, warm, glowing ones, provided the rare alignment happens to occur while astronomers are watching. The trade-off is that microlensing events are fleeting, often lasting only hours or days, and once they're over, the specific planet responsible is essentially gone, lost somewhere in the vastness of the galaxy, with no practical way to relocate and study it further, at least not with the methods available before Subo Dong's team figured out the Gaia parallax trick. That's the deeper reason the KMT 2024 BLG 0792 measurement mattered so much to researchers like Gavin Coleman. It wasn't simply one more data point added to a growing list. It represented, for the first time, a way to extract real, lasting, individually verified information, distance and mass both, from an event that would otherwise have vanished from view within days, never to be observed again. Every rogue planet found through microlensing before that point existed in the scientific record only as a statistic, a brief flicker contributing to a population estimate. KMT 2024 BLG-0792 became something closer to an actual, individually characterized world, with real, specific, measured properties. The same basic kind of information astronomers have long been able to gather, for planets that have the convenience of an orbiting relationship with a bright, easily observed star. It's also worth circling back to PSO J318.5-22's proximity, because 80 light-years genuinely is close by the standards of this entire field, and that proximity raises an interesting point about how much closer some of these objects might be hiding, completely undetected, simply because they're old enough and cold enough to have faded below the detection threshold of any survey conducted so far. If a 6 to 8 Jupiter-mass planet, 12 million years old and still warm enough to glow in infrared light, was sitting just 80 light-years from Earth before anyone noticed it, simply because nobody had looked specifically for it using the right instrument and the right search criteria, it raises a genuinely open question about how many older, colder, completely dark rogue planets might be sitting at similar or even closer distances right now, drifting through our own stellar neighborhood, with absolutely no way for current telescopes to detect them at all. This is precisely the kind of gap that the Nancy Grace Roman Space Telescope and the extremely large telescope are being built to start closing, pushing detection sensitivity down toward exactly the kind of older, fainter objects that have remained functionally invisible throughout the first 25 years of this field's existence. One last thread worth pulling on before closing this out involves the panspermia idea raised earlier, the speculative notion that a rogue planet carrying a hidden subsurface ocean and whatever life that ocean might contain could drift close enough to other star systems over the course of its journey through the galaxy to potentially contribute to seeding life elsewhere. It's important to be clear that this remains one of the most speculative ideas discussed in this entire video, sitting well beyond anything that's been directly tested or confirmed. But it's worth understanding the basic logic behind why researchers take it seriously enough to publish on it at all. A rogue planet, unlike a planet locked into a stable orbit around a star, isn't confined to one small region of the galaxy for its entire existence. Over the course of hundreds of millions or even billions of years, a free-floating planet drifting through the Milky Way could, in principle, pass through or near numerous other star systems over its lifetime, each pass representing a small chance, however statistically remote, of some kind of material transfer or gravitational interaction with that system. Multiply a small chance by an enormous number of potential rogue planets, each with potentially billions of years to wander, and countless star systems scattered throughout its path, and even an extraordinarily unlikely event starts to look at least plausible across the full population, rather than for any single object. None of this changes the bottom line established earlier in this video regarding Earth's own safety from rogue planets. The same vast distances and low probabilities that make a direct collision or close gravitational encounter with our own solar system so unlikely, the 1 in a billion odds over the next 1,000 years, calculated by researchers like Cassidy Ward, apply just as much to scenarios involving panspermia or any other kind of meaningful interaction between a passing rogue planet and our own system. The galaxy is, despite everything covered in this video about how many rogue planets likely exist within it, still an overwhelmingly empty place. And the sheer scale of that emptiness is exactly why these wandering worlds can exist in such enormous numbers while still posing essentially no realistic threat or interaction risk to any particular star system, including our own. What all of this ultimately leaves us with is a population of worlds that exist almost entirely outside the boundaries of what astronomy, until fairly recently, considered to be the basic definition of a planet. It leaves us with a category of object that simply didn't exist in any confirmed, scientifically established sense before the year 2000, and that has, in the relatively short span since then, gone from a single ambiguous detection to an entire population numbering, by the most credible current estimates, somewhere between billions and trillions within our galaxy alone. It leaves us with direct evidence, from PSO J318.5-22 to OTS 44 to CHAR 1107-7626, that these worlds aren't simply frozen, inert leftovers drifting through empty space, doing nothing of interest. Some of them are still actively forming, pulling in raw material at rates that rival or exceed anything seen around actual stars, generating their own magnetic fields, cycling through chemistry typically associated with stellar birth, all while having no star anywhere nearby to influence or guide any of it. It leaves us with a genuine, unresolved scientific controversy in the GEO-MBOs, an entire proposed category of paired planetary objects that may either represent one of the strangest formation processes ever documented in modern astronomy, or may turn out to be an elaborate case of mistaken identity involving distant background stars, a question that the field has not yet definitively settled and that will likely require additional observations to resolve. It leaves us with a real, physically grounded, but entirely unconfirmed possibility that some of these worlds, whether through dense hydrogen atmospheres acting as thermal blankets, or subglacial oceans warmed from within by radioactive decay, or large moons kept warm through tidal heating, could theoretically sustain liquid water and potentially even life, completely independent of any star, anywhere, ever. And it leaves us with a reassuring, well-supported answer to the one question that probably matters most on a personal level. No, none of this poses any meaningful threat to Earth. The odds of a rogue planet even entering our solar system within the next 1,000 years sit at roughly 1 in a billion, according to researchers who've actually calculated the relevant probabilities, and the odds of one ever posing a direct threat to life on Earth specifically are smaller still. Whatever else is true about the staggering numbers and strange behaviors of these wandering worlds, they remain, as far as the science currently shows, exactly what their name suggests: distant, isolated, and almost entirely disconnected from anything happening here. What this story ultimately comes down to is a quiet but genuine shift in how astronomers, and now, hopefully, you, think about what a planet actually is. For most of human history, a planet meant something that circled a sun, something defined entirely by its relationship to a star. The research covered throughout this video, built up patiently over 25 years, across microlensing surveys in New Zealand and Chile, direct imaging campaigns in Hawaii, 20 years of archived data from the Canada-France-Hawaii Telescope, an unprecedented infrared survey from the James Webb Space Telescope, and a clever parallax trick using a spacecraft sitting nearly 1 million miles from Earth, has shown that a planet doesn't actually need a star at all. It just needs enough mass, the right formation history, and, apparently, an entire galaxy's worth of room to drift through, alone, sometimes for billions of years, carrying whatever heat, whatever chemistry, and possibly, on some still undiscovered world out there in that vast and largely unmapped population, whatever life it happened to be born with, or to capture along the way. These are the planets that wander the galaxy with no sun to call their own. And as the next generation of telescopes comes online over the next several years, the Nancy Grace Roman Space Telescope, launching in August of 2026, China's Earth 2.0 mission, following in 2028, and the extremely large telescope, continuing its construction in Chile, the billions to trillions range that currently defines how many of these worlds actually exist out there, is finally positioned to start narrowing into something far more precise. 25 years ago, astronomers weren't even certain these planets existed at all. Today, they're measuring their masses, their distances, their growth rates, and their magnetic fields, one faint, isolated, starless world at a time. Whatever comes next in this story is likely to be stranger and more precisely measured than anything covered here, and given how this field has moved over the past quarter century, it probably won't take very long to find out.